advantages of microfluidics. That's portable because it's so small and so compact. You have reduced analysis time and you have very small sample sizes. Now, because of this portable technology, um, usually you want to mix well. And so I guess one of the biggest advantages of fast mixing is that quick chemical analysis that I talked about to reduce analysis time. And for example, you see previously we talked about this Christmas tree method, a way of mixing fluids by using intricate channeling, and the output produces a gradient. Now, since microfluidic channels are small, and to review a little about the Reynolds number, because of how it is, the Reynolds number is usually less than 100. And now, since it's less than 100, most flow within the microfluidic channels are laminar. And now, since most of these flow is laminar, they create the only way to kind of mix fluid is by diffusion. Laminar flow really isn't that good at mixing, just only diffusion is the best method. And from the paper, one of the approximate times for diffusion is using the L, which is the distance to diffuse, squared over D, which is the diffusion coefficient. So I guess, what are some methods that microfluidics use for mixing? So some of the methods, like I showed before with that Christmas tree, is the intricate channeling. You can use a zigzag approach, or you could have two fluids flow through a channel and then combine later on together. There's also creating plumes, which is basically injecting one fluid into another. So with the nozzle. So now this nozzle, once you inject it into the other fluid, it kind of has all this contact surface that allows the fluids to diffuse with each other. On top of that, there's also, I guess, external sourcing. So what other ways, I guess, to mix methods than using external methods? There's a lot of these methods. Sometimes you can use magnets, sometimes you can use sound, acoustics, like I mentioned before. However, let's talk a little about this, right? So the biggest reason you want to use the external mixing method is to introduce chaos, right? So one good way of mixing, like for example, if you have like a mixing two drinks together, is to shake it up to introduce chaos into the system. That's one way of mixing without diffusion. So there's some methods. One of them is called dielectrophoresis, or DEP, which produces electromagnetic waves on dielectric particles. And what happens is these electromagnetic waves are not balanced. So since they're not balanced, the force exerted on these particles, there's a net force, and it allows the interface between the two fluids to kind of bend and fold on top of each other, and basically. However, this requires electrodes to be under the channel. Usually you want an insulating layer between the electrodes and the channel. There's also high AC electric fields, which is applied through platinum electrodes, which also is a decent method. However, they usually use low frequency AC voltage, and the biggest thing is that it requires a lot of voltage, around in the kilo, so 10 to the 3 volts for any effective kind of mixing. On top of that, there's also magnetic stirrers, which uses magnets to kind of stir the liquid inside. However, they need a rotating magnetic field, and for that, usually need a decently sized apparatus. So the use of microfluidics for small portable technology wouldn't work really well. Another method is ultrasound, right? Similar to acoustics, which uses some type of hydroelectric disc and excites the air bubbles trapped in the top layer, which allows the fluid to move. However, this also produces like unwanted heat and things like that. But to dig deeper into this ultrasound, let's talk about acoustic streaming. So this experiment mostly deals with the ultrasound part, though isn't exactly this exact method where it excites air bubbles. So to the apparatus of how this experiment is made, how it works is, see this, let's see, you can see my mouse. So this little 50 micrometer thing right here, that's the channel. and that's made out of PDMS. And this PDMS was activated for 30 seconds in this oxygen plasma. And now this ultrasound transducers are under these quartz wafers. So the reason why the PDMS was activated for 30 seconds under the oxygen plasma is because it allows for better adhering between the PDMS and the quartz wafer. So once the 30 seconds was done, the PDMS microchannel is stuck on top of the quartz. So this experiment is actually made for 2 inputs, and as you can see, these little blocks right here, these are the electrodes. These black blocks right here, one right here, right here, and right here. So they're evenly distributed in terms of space. However, there's different electrode patterns, and one of the biggest reasons is because they want to observe how the pattern of the electrodes affect how well the mixing goes. And then on these transducers, there's a high frequency signal generator. So that's the acoustic part, right, or the ultrasound part, where it sends sound into these transducers and it goes through the quartz and hits the microchannel. That's what creates this, introducing the chaos or the sound into the system. Okay, so let's talk a little about the mixing. So first, what the general idea of the experiment is, 2 fluids are going to come in right here, channel 1, channel 2, and they're going to converge into a main channel. And once they converge into a main channel, it's going to use a pH indicator and a base. So the pH indicator on the bottom shows over here, phenolphthalein, as you know from like chemistry. The base is sodium hydroxide. And those two both are clear solutions. You can see a little goldish color. However, that's just from the camera. But they're both clear solutions, and once they interact with each other, the pH indicator shows a pink color, as you can see from this interface right here. The frequency that was at the transistor is on 445 megahertz, max power level of 15 decibels. The input flow rates would be between 2 and 30 microliters per minute per channel, meaning that every channel, each individual channel, the input channels, not the main channel, would have these flow rates. And then once it flowed through this black box right here is a transducer, and the flow would go from left to right. Now, let's look at some of the results, what happened in this experiment. So the same picture that you saw right here, this is actually a zoomed in version on the right side. Now, as you can see, these are 2 different scenarios, one with different flow rates. This is around 10 microliters per minute, the right side. This is 60 microliters per minute. So it's interesting because the one with less flow has more color, more pink, quote unquote, or color uniformity. Or on the left side, it doesn't. It has less, even though it's 60 microliters per minute. And similarly, so remember how there's different pattern electrodes? So these 2 right here were actually the first transducer, and this was the 3rd one. And they kind of showed what happens here. However, they found out that in general, the first pattern, this checkered-like pattern, was one of the most effective ways of creating the most uniformity of this of the mixture. Right. So now here's some of the data and all that. But so to go over it, this graph shows the distance, 100 micrometers from the leading edge of the transducer, and with the red level right here, which is the red level's intensity. So right here, a red level of 90 is ideal. So one thing that they did in the experiment is, okay, more intensity doesn't necessarily mean more, what is it called? I guess more uniformity. So what they did was, before doing the experiment, they actually mixed the 2 solutions together, And then once they mix it together, they ran it through the channels and observed the red level intensity. And they found out that it's around 90, the red level that they get. So a red level that's around 90 would give you the best uniformity. So I guess it's hard to see because I kind of blew up the graph a little bit. But this solid black line right here, this would give you the 4 microliters per minute. Right on the bottom of that would be the 10 microliters per minute. On top of the solid black line is 20. And all the way on top right here is the 60 microliters per minute. So they observed that over 50 microliters per minute, um, that the uniformity kind of degraded. It didn't really touch that 90 red level. Um, and yeah, so they found out that, oh, okay, it's not good. But yeah, so they found out that exactly, so more flow rate doesn't necessarily mean more uniformity. Um, so there is a certain flow rate to match the frequency of the electrode or the power level that's outputted by the transducers. Um, so some takeaways from this experiment. Um, so the primary mechanism for mixing is acoustic streaming. Um, so the way this works, here's a couple of equations. There's the Langevin acoustic radiation pressure. This is mainly what we're concerned with. So this the acoustic radiation pressure kind of shows, oh, okay, more. So this has the pressure over here, and this is the input for the PI. And so they found the source of the sound, right, as you remember from the transistors are from the bottom, right? So it's from the bottom and it's producing a sound right here. So the bottom is technically over here because its quartz is that insulator between the electrode and the transducers. So at the bottom would be right here, and the top would be that 50 micrometers, so the height 50. So because sound is emitting from the bottom to the top, there's going to be a loss. There's going to be acoustic absorption, that they call it. And what happens is because it's acoustic absorption, there is a pressure differential from the bottom to the top. So now, since it's perpendicular to the flow, and there's a pressure differential, you know that flow is driven from this pressure differential. So it creates this an upward, like an upward flow velocity or vertical flow velocity. And so at the bottom, it was calculated to be around 816 kilopascals. Top was around 612 for this right here. So the radiation pressures were 148 and 83, which is around 60, 65, oh, sorry, 65 pascals of pressure differential. And the calculator from that, the vertical flow velocity would be around 85.7 centimeters per second. Although this is the calculation, this is a rough calculation. This should be more to look at the order of magnitude rather than precise vertical flow because it has a lot of assumptions. For example, it doesn't take into account that since sound is being produced, there's going to be standing wave patterns. And once they collide with each other, it doesn't take into account how that standing wave affects the fluid flow, since these are microchannels. Okay, and on top of that, so again, this is acoustic streaming, which is perpendicular to the flow. Now, they found out acoustic streaming is pretty an effective way of an external source for mixing. It's very minimal. Transistors are very small. They're on the bottom of this quartz. It's not like something like where a magnetic stirrer needs a decent sized apparatus. It's pretty portable. And although the sound comes from the bottom to the top, the mixing is still delayed in the order of microseconds. So it's still fine for the mixing itself. It doesn't have a huge delay, which can, since it's only 50 micrometers, the delay is pretty negligible. On top of that, like I said before, right, the checkered pattern was to be the most effective in terms of acoustic, in terms of uniformity. Reason being is because this allows every little pocket of fluid to kind of mix with the other side of its laminar of the other fluid. And yeah, usually so ultrasound mixing, usually they form bubbles and they heat the fluid up, unwanted heat. Uh, from this experiment, they didn't observe any bubbles. And they assumed that negligible heat was here because they did an experiment before, and they said that they had 3 times more power, and it didn't produce that much of a temperature difference or temperature increase, and so they assumed the same thing over here. And then also, as I said, so around 50 microliters per minute, the uniformity degraded. So to account for a higher flow level, they would have needed more power to, I guess, to have the same amount of quote unquote uniformity. Yeah, and then that mostly is it for the references. Mostly is it for my presentation. Do you guys have any questions?
Okay, great, Brian. Thank you for your presentation. Any question?
Brian, can you go back to like a little bit more back toward the beginning, actually, with the results? Yeah, there. Can you re-explain to me what the difference between these two exactly?
Yeah. Oh, it's so it's the same thing. So it's the same first transducer. So remember how there's different patterns? It's this one right here. But the only difference is the right side is these are different flow rates. So this is 10 microliters per minute, and this is 60. So this has more flow rate, but you can see it has less uniformity. Yeah. This has less flow rate, but it has more uniformity.
Do they explain why that's the case?
They didn't explicitly say why, at least from what I was reading. But I assume that because from what I think, probably because if you have a higher flow rate, and so it's giving a, what is the exact number, sorry. So the frequency, so the frequency is the amount of times the sound is produced or the waves are produced per second, is around, it has a set frequency and it has 2 flow rates. Now, because if you have the same amount of time to produce the same frequency, you have 2 flow rates. If one is faster, it's going to shoot more fluid out at the same time than if you were to do the slower one. So I guess it's kind of confusing, I guess. So in this pocket right here, for example, right, you have 10 microliters per minute. That means more fluid is interacting with these transducers. Whereas over here on the left side, you have a higher flow rate, so less fluid will be interacting with the transducers. That's my deduction. I'm not exactly sure.
And you said that and you're saying that the electrodes are actually causing the mixture of the fluid by waves. I'm trying to okay.
It's similar to similar to like a speaker where it sends sound, quote unquote. Right. And these electrodes basically send the vibrations over, and these stabbing patterns that are created goes from the channel, and it's perpendicular to the flow, so it goes from down to up, right? Because the sound will be emitted like a wave-like pattern from bottom to top, while the flow is from left to right. Yeah.
Makes sense.
Yep.
Do you think viscosity is playing a role in it? As in, like, with the fast-flowing fluid, viscosity is dampening the spread of the fluid, and hence, like, it's not mixing up properly.
Yeah, I mean, viscosity always plays a role in fluid properties. In terms of the time for diffusion, I think viscosity, I haven't looked too much into it because I did get the paper very recently. It deals with the diffusion coefficient, so it definitely deals with it. Viscosity is already dominating, though. That's the thing. It's laminar, and because of this viscosity, it's not going to really have too much chaotic flow because it's microfluidics, very small fluids. But yeah, viscosity, I guess, has a play. Yeah.
So in terms of the different effects for mixing between these 2 cases, well, as Brian mentioned, because the ultrasonic wave is perpendicular to the flow direction, so we can think about the extreme case, if the flow rate is so high that, well, the pump immediately force the fluid to flow downstream, then the ultrasonic wave doesn't have enough time to even induce the mixing in the lateral dimension. Right?
Exactly, yeah.
So
That's why they would
sense.
need, that's why, I guess, sorry, to add on a bit, that's why you would need more power. So you would have, I guess, like a higher frequency for it to resonate properly. Yeah, for the higher flow rates.
Yeah. Also, I have a question about the graph that you showed between red level and distance. Yeah, this one.
Yeah.
So what distance exactly? This one.
So distance, oh, I should have put it to the left, but the distance is actually 100 micrometers from the edge of the transducer. So it's not all the way from the beginning.
Can you show it from the?
Yeah, sorry. So here's 2 millimeters, so that's 2,000 micrometers. So obviously doesn't make sense. It would be right. So basically 100 microliters from this edge right here, from the first electrode. So you can see from the graph that there's not a lot of activity until it hits 100, then it starts to rise and the transducer starts doing its work.
Is this the width? I mean, the 600 micron in total shown in this graph, is that the width of the channel, or which direction is this, from 0 to?
It should be from the flow direction.
From flow direction.
Yeah. It wouldn't make, I mean, the width isn't too important. We're talking about how the transducers go from left to right. And this deals with the first transducer specifically. Yeah.
I have a question.
Yeah, go ahead.
Just to clarify what the professor was saying earlier. So as the flow rate increase, the frequency needed for mixing also needs to increase.
Yeah, in general, it's not that simple. The paper, I think, goes a little bit in depth with it, which I don't think is too necessary for our cases. But yeah, there's like a certain resonance frequency that allows you to have, I guess, the maximum power output. But yeah, in general, the frequency does have to increase for a higher flow rate. Because the flow, if you could think about it, the flow is going faster through these channels. So you want to have a higher frequency for these sounds to get out, or for these sounds to interact with the fluids to allow the mixing.
Okay.
Yep.
Can you go to the slide with the graph for a second, please?
Graph, yeah.
All right.
Is any more questions or?
Okay, so if no more question, let's thank Brian again for his presentation. Yeah, our second speaker would be Mohammed.